right, folks, let's go ahead and get started. So last time we spent the bulk of the time simply looking at the directional derivative. And just as sort of a refresher here, let's just take a look back here. We've got a function. So let's look at number 18, and I've got copies up here. If you need one, come on up and grab one. Number 18, we've got a paraboloid, and we want to compute the directional derivative at for two different directional vectors. So the thing to keep in mind is that this statement here, computing a directional derivative, here you go, Ben. That's right. If you want to compute a directional derivative, you could go through this long, nasty limit definition. Okay? And I think that in your, let's see, did I do it or did I have you watch it? I don't remember which. I think that I had you watch it. Yes, we did this. You guys watched this in 23. We showed that rather than doing the nasty limit for the directional derivative, we can simply take the gradient and dot it with our direction vector. Okay? And we'd already kind of given a hint to that. And so rather than doing this computation here, which involves using this long limit, we instead compute the gradient evaluated at the point dotted with that unit vector. And that's a far easier calculation to do. So for our function here, we need to calculate the gradient of f. And the gradient of f would be what? Well, first of all, folks, I think that at this point in the course, it's now, before you do anything, any sort of computation, you should ask yourself, what object am I working with here? Okay. We actually don't have a name for the gradient on its own. We will eventually call it a vector field. Okay. But certainly the gradient at a point gives us a what? What type of object, folks? It's not a scalar. The directional derivative, after we do this dot product, will eventually give us a scalar. It gives us a vector. Okay. If you've forgotten that, I need you to review that. I need you to review the idea that we've got a surface, and we'll be talking about a point in the domain, and the gradient will be a specific vector in the domain that points in the direction of what? It points in the direction of steepest descent. Okay? So before you go doing any computation in this class going forward, you need to just double check that you know what types of objects you're working with. Otherwise, you could just be doing math for math's sake and you have no idea whether you're on the right track. Okay? So here we want to compute the gradient. How do we compute the gradient? Well, it's partial f, partial x, comma, partial f, partial y. Now, folks, what if I want to compute the gradient of a function of 3 variables? It'll be a vector, or another way of saying that is a vector field, but it'll be a vector where the first coordinate function is the partial derivative of the first variable, and the second coordinate function is the partial derivative of the second variable. And so if I have a third variable, it would just, the third coordinate would be the partial derivative of the third variable. Okay? And so you can take gradients for any function of multivariable function. Okay? So in this case, we would end up with taking this gradient. Notice we get 2. It's got a quarter multiplied in front of it. So I think we get looks like 1/2 x comma y for the gradient. That's the gradient as a vector field. The way I want you to think about it is it takes the entire domain space, and at any point in the domain space, it gives me a vector pointing in the direction of steepest ascent in the domain space. So this would be the gradient of f at some other point, x naught, y naught. This would be the gradient of f at some other point, x1, y1. And so this is a set of instructions for how to get the gradient at any point in the domain. Okay? But we're specifically computing the directional derivative for this function at the point 3, 2. So we're going to evaluate the gradient at the point 3, 2. If we do so, we end up with 1/2 times 3, 2. And so we end up with the gradient being 3/2, comma 2. There's the gradient at that particular point. Okay. We can now go compute the directional derivative. Okay. So if we go to compute the directional derivative for the vector u of f at the point 3, comma 2, we're taking the gradient of f at 3, comma 2, and we're dotting it with our vector u here. Now, be careful here, folks, because sometimes the way the problem's presented to you, there's not a whole lot, there's not an extra step. What do we always need to check when we're dotting the gradient with a vector? Exactly, we got to make sure that the vector that we're dotting it with is a unit vector, that its magnitude is 1. Okay? So in this case, we're going to dot it with the vector 1 over the square root of 2, comma 1 over square root of 2, and I noted that these were unit vectors. If they weren't, I would have to give the equivalent unit vector. Okay? Don't miss that step. So then we've got the vector 3/2, comma 2, dotted with 1 over the square root of 2, 1 over square root of 2. If we do that computation, we end up with, oh, no we don't. Charles, what mistake did I just make, folks? Maybe you didn't see it. Well, I said before you do any computation in this class, you should ask yourself what? What type of object are we getting? What am I about to do, folks? A dot product, so I'm getting a scalar. Okay? So we end up with 3/2 times 1 over square root of 2 plus 2 times 1 over the square root of 2, which gives us 3 over 2 radical 2 plus 2 over radical 2. And I'm just going to park the answer there. Okay. How we doing, folks? Okay, yay, nay? Now are you saying yay just because? Let me ask you this question. What is it that we just found? Well, I mean, one answer is we just found the directional derivative. But what does that mean, folks? Does anyone want to take a shot at explaining that? What does it mean when we say the directional derivative for the function f at the point 3, comma 2 for this directional vector is whatever that sum comes out to be? And I think in the notes I gave you a decimal approximation of it.
It's the change in z when we move in the 3, 2 direction in the domain.
Exactly. So just to give us a, oh, here's the picture right here, and there's the decimal approximation, 2.47. So what we're saying here, folks, is if I go to this point in the domain, and I take my compass, which gives me a vector pointing in R2, right? I take my compass, and I go in the direction of this unit vector here. If I were to take one step in that direction, I would expect my z coordinates to rise by 2.47 units, approximately, right? The only reason why I'm saying approximately is because I don't act, that's my instantaneous rate of change, and through the process of taking that one step, the instantaneous rate of change actually changes as we go through that. That's what I mean by approximately, right? Okay. But roughly speaking, you're saying, hey, if we're on this piece of terrain, if we move in this direction, if we took one step, I would expect my elevation to change by about 2.47 feet. Positive. So I'm going uphill as I step in that direction. Okay. Folks, I have nothing more to add to this idea of the directional derivative. Okay. Now, that doesn't mean that the things I said weren't important, and it also means that probably there's some stuff that I said that you didn't quite hear. Okay. So you need to do some work with this. You need to rework through these problems, and then come let me know what your questions are. Because otherwise I would just start the lecture over and repeat myself. Okay, so you've got to go figure out what your questions are about this, because it takes some time to get comfortable with this directional derivative. I feel like at this point in the course, we've now introduced all sorts of new objects. Okay? It's like after yesterday's lesson, we introduced all of these new things we could talk about. Where is it here on the last page? Come on. All of these new things we could talk about. We've got the gradient as a function, we've got the gradient at a point, we've got a directional derivative of as a function, we've got a directional derivative at a point, we've got all sorts of things we could talk about here now, and that's going to take a while for you to absorb. Okay? All right. So that's a quick reminder of the directional derivative. At that point, we don't really have anything more to say about the directional derivative, but there's a lot to do with this gradient. And last time we did a nice slow exploration as to why the gradient is a vector that points where? In the direction of steepest descent. It's saying, hey, I'm standing on this piece of terrain here. Which way could I go so that I'm going to have the steepest climb? And the gradient points in that direction. So, folks, to me, that's good enough if I tell you that. But let's just double check. If I want to say, what direction is the direction of steepest descent, what direction is that? 180 degrees from there, the opposite. So we take the gradient and multiply by -1. That gives me the direction of steepest descent. Okay? Then, if I actually want to know what that rate of steepest descent is, or what that rate of steepest descent is, I'm going to take the magnitude of the gradient. That gives me what that rate is. Okay? So remember, the gradient says go that way if you want to rise the fastest. The magnitude of the gradient says if you step that way, you'll be climbing this quickly. You'll be climbing at this rate. So the magnitude of the gradient vector tells you the rate of change in that direction. How are we doing, folks? All right. So then, let me see where we are. Oh, so then last night, I told you, I'm sorry, folks, but I just need you to work through these. So this is what should convince you that rather than computing a directional derivative, you can just take the gradient and dot it with a unit vector. This next one brings up this incredibly important mathematical fact. Okay? So number 24 here brought up this incredibly important mathematical fact that says that the tangent line, that says that the gradient, as long as it's not 0, the gradient always points in a direction that's orthogonal to that point's level curve line. Okay? So if I were to give you some level curve lines, for a function, okay? And then I guess what I do need to tell you is what directions increase. So maybe this is a z naught equals 10, this is a z naught equals 9, this is a z naught equals 8. Then if I go ahead and say I want to talk about this point right here, AB, you should be able to now place the gradient on this domain. Now careful, folks. All of this is talking about the domain space, right? I'm talking about the domain. These are the level curve lines. They lie in the domain of this function. There's some surface lying above this that I've projected down here. I guess it's a, kind of like if you were to look down on it, it looks like a mountaintop that we're looking down on. But I'm saying in the domain, we can compute the gradient. Where's the gradient? Well, this tells us the gradient is always orthogonal to the level curve lines, these lines that I just sketched here. So where's the gradient? Well, there's the tangent line to the level curve line. That's not the gradient. That's a tangent line to the level curve line. So where's the gradient? The gradient is pointing, we need a color we haven't used. The gradient is pointing this way. What is that? That's the direction of steepest ascent. What if the gradient were longer? That would mean that your climb is even steeper. If the gradient were shorter, then that would be your climb, while still the direction of greatest ascent, is less steep. Good catch. Gabe's about to tell me, wait a minute, that's not the direction of steepest ascent. Which is the direction of steepest ascent here, folks? Because I labeled these curve lines on here. That's the direction of steepest ascent. How we doing, folks? Absolutely essential that we have that fact at the ready whenever we need it. What does the gradient do? Well, it points in the direction of steepest descent. That means that it's always perpendicular to our level curve lines. Okay. Based on that, okay, we can first talk about this idea of the curve of steepest descent. Okay. In my domain space, I can give you a set of x, y points that trace out a curve that will take me in the direction of steepest ascent. Okay? Again, the mountain lives over here, lives above this. The path you take will be some path on the mountain. Okay? But this is the route that you take in the domain space to trace the path on the mountain that climbs the mountain at always taking the steepest route up. Okay? To be honest, folks, I'm having a hard time thinking of times where you want to take the steepest route up in kind of the, well, first of all, when you're climbing a mountain, that's probably not the best thing to do. But also just like a story problem that you'd want to do this. But I can think of lots of things that take the steepest route down. For example, water takes the steepest route down a mountain. So if you want to model water running through terrain, you're going to use the gradient path of steepest descent. And you can model that then. Okay? In order to do that, though, we have to solve some differential equations. Okay? So we had this one here, and in the video I derived this differential equation here. That differential equation, it gives us a parameterization. The solution to that differential equation is what we'll need for a parameterization of our level of our contour curve. Okay? If I give you just this is the level curve. And if I give you all of this, all 3 dimensions, this is the contour curve. So this is the path in the xy domain space that I should take in order to stay at a level on a contour line on my function. Okay? Of course, once you've got an x-coordinate and a y-coordinate, how do you find the corresponding z-coordinate for a function of that inputs 2 variables? You take those 2 values and you plug them in to the function. That's where we're getting that 3rd coordinate from. So that shouldn't be a mystery, that part there. Okay? Where did this differential equation come from? That was from the video that I had you watch. Okay? So if you didn't watch those videos, shame on you. Go back and watch them. Okay? And so this gives us our way of coming up with the level curve lines. That is, imagine this mountaintop up here. It tells me the path that I should take to go around this mountain without ever changing my elevation. Okay? And you could dream up scenarios where that might be a useful thing, right? Like, so maybe the function, rather than being a mountain, is telling you the amount of radiation that you're being exposed to. Okay, you want to take a path so that you're always keeping the radiation level the same as you move through this field, or what, I don't know. I'm trying to come up with an example there. Okay. This differential equation here, which is different, take a look at it. See how they're different? Okay. How are they different? We talked about this in the video. What's that? No, that's not the only way. They are what of each other? They're negative reciprocals of each other. Does that make sense? Excuse me. Does that make sense? Does it? Does it? What does this differential equation do? It gives us the it's basically solving for an equation that will keep us along a contour line, or a level curve line, or a contour curve, right? What does this do? This moves in the direction of the steepest ascent. It's the gradient direction. Does it make sense that these 2 are orthogonal to each other? Look at this. It's the negative reciprocal. That's what you do when you find a perpendicular slope. That's exactly what this said, right? The gradient is always orthogonal to a level curve line. Okay. So with all of that, we can now go ahead and do some of these problems. Okay. Here I ask you these 2 questions. These are 2 good questions to work through. Folks, I think Anna caught an error in the, no, it wasn't in D. It was in C. There was an error in the solution to C. Basically what I did was I took the number 61 and added it instead of 57, which I had found earlier. Okay. What I'd like to do, though, is let's work this problem here. So this function, let's go look at it again. What does the graph of this function look like, folks? I expect you to be able to identify that now. A what? Elliptic? Elliptic paraboloid, right? It looks like z equals 4 plus x squared plus 3y squared. So if I go look at the trace, If I go look at the trace in the y equals 0 trace, that's a parabola. If I look at the x equals 0 trace, that's a parabola. And if I look at the z equals 0 trace, I get nothing, right? There's no solutions to that, right? Take a number, square it, take a number, square it, add 4 to it. There's no way that'll ever equal 0. But as soon as z gets large enough, we start getting, like if z were 10, would you mind grabbing the door? Thank you, Andrew. As soon as z gets large enough, then we end up getting elliptical curves for our traces. So this is the graph of an elliptic paraboloid. Great. Okay, so what we're going to do now is we're going to take, for this elliptic paraboloid, I'm not going to worry about exactly drawing it correctly, but there's this, it's got a +4. Okay. There's this elliptic paraboloid, and we're going to take a ball at the point 3, 4, 61. Well, that'd be right about there. There's the point 3, 4, 61. And this is a little bit, I mean, the ball is not actually on the surface, right? The ball would like be rolling along the surface, so this isn't quite 100% true to life. But we're going to set a little ball where that point is, and we're going to release it. Okay. And we're going to model its path as it goes through there. Okay. So in order to do this, what do we need to do? Well, we're going to take and project this down. Well, so what we're going to do is we're going to go down into this space here. This is the domain space where we've got 3, 4 in the domain space. And we're going to compute the gradient, which will tell us where the ball will start rolling. Then we'll step in that direction, recompute the gradient, and then step in that new direction. Okay? And what that's going to do is that's going to give us a path in the domain space. And then if we look at how that path corresponds to a curve in the range space, it will tell us how this ball falls. And I would have thought, before I computed this, that the ball would head like directly towards the center, but that's not true because of the elliptical shape of this elliptic paraboloid. Okay? So what do we need to do? Well, if we want to find the curve of steepest descent, we need to solve a certain differential equation. What was that differential equation? dy dx is equal to, it's on the previous page, what's that differential equation for steepest descent / descent? F sub y over f sub x. So in our case, let's see here, sorry folks, I forgot to copy it. We've got f sub xy is equal to, I think it was 4 plus x squared plus 3y squared. Is that correct? Do I have it? Yep, okay. So then we're going to be solving the differential equation. dy dx is, if I take the partial derivative with respect to y, I get 6y all over the partial derivative with respect to x, and I get 2x. Now, some of you may not have done a differential equation in a while, or that's perfectly fine. This solution is just, it's kind of like integrating in that we will get a family of solutions when we solve this differential equation. What we want is to select from amongst that family the one that has a specific, passes through a specific point. And the easiest point to use is the one that I gave you. So we know that y sub 3 needs to equal 4 when I solve for the function y. Did everyone see that? So this is the differential equation. This is the initial condition that we need. Okay? And for those of you curious, there's a whole course in mathematics that goes into the theory of solving these differential equations. This one is not too bad. This is what we call a separable differential equation, which means it's possible to rearrange this and just integrate both sides. Okay? So that's as hard of a differential equation as I'll ask you to solve in this class. So if we go ahead and separate this, we could rewrite this as dy divided by 6y is equal to dx divided by 2x. There's actually kind of a lengthy explanation that justifies what I just did, but at the end of the day, what I just did symbolically works, and it gets me to the right answer every time. So we just do it. Okay? What I'm saying there is I treated the differential operator as if it were a fraction, and I moved the numerator and denominator around. That's actually not a legal move, but it's something we all do anyway. Yes?
I was just going to ask if I could factor out competition.
Oh yeah, you certainly could have reduced that down, and maybe I should have done that right from the get-go. I like it. Well, I've started, so we'll just say, that, yeah, you certainly could have reduced this down to 3y over x, definitely. Okay? And so that means that probably something we'll divide out later on, too. Okay? So now what we do, and this is kind of a weird step, is we put an integral symbol on each side. That should seem strange. Okay? There's nothing wrong with integrating both sides with respect to x. But it should seem strange to just put an integral symbol on each side of an equation. Again, that's something that you justify once, and then you never justify it again, and you just do it. Okay. So what we end up with is, this would be the natural log, let's see here, I guess 1/6 natural log of 6y is equal to 1/2 natural log of 2x. And let's see, let's clear out our fractions by multiplying both sides by 6. So we get that the natural log of 6y, I'm going to drop the absolute value here, folks, because this is going to end up being positive, is this. Then we go ahead and exponentiate both sides. So if I raise both sides over e, I'll write it this first time because I guess we haven't done it in this class. So usually you don't write this step, you just do it. So this is going to give me 6y is equal to 2x to the third power. How did I get third power, folks? By properties of logarithms, I put that natural log, I brought the factor of 3 in as an exponent, and then I applied my identity properties. So then we end up with y is equal to 1/3 x cubed. Oops, I made a mistake here, folks. Sorry, I'm rusty with my differential equations. Plus c, right? Because I integrated both sides. Where should I put that? I got to go back and catch this up. Sorry, folks, I got lazy here. I should have a plus c here, a plus c here, a plus c here. Oops, but that would mean that when I go to exponentiate both sides, what I should have ended up with was this expression and an e to the c, which we just give a name as a different constant. And so that's where that constant shows up.
And do we not need a constant on the other side?
Correct. So usually what you do when you do these problems, Dave, is you've integrated both sides. That gives you an arbitrary constant on each side. Then collect the arbitrary constant to one side, and you just so we just kind of get in the habit of just putting plus c there. I think some people might have a question though. How did I go from here to here? Should we talk about that?
Yes.
Yeah, let's talk about that. How did I go from here to here? So this would be, this is the same thing as e to the natural log of 2x to the third power times e to the c. Do you buy that? By the properties of exponentials, this is the same thing as this where the plus c is up inside the power there, right? We okay with that? Okay. But then, and this is a trick that all math people do. This maybe we give this constant a name like c sub 0. But what's an arbitrary number over, or as an exponent of e? What's that going to give me? Another arbitrary number, and so we would maybe put c1 there. But in math, when you have what we all kind of do, and we get a little lazy, when you get rid of one constant, you just have one constant, you just keep calling the new constant c until you actually have to keep track of it. Which sometimes you do. Sometimes you do have to keep track of the constants. But here, this is just another arbitrary number. Okay? Yeah?
2 cubed is 8, so then 8 over 6 would be different than 1/3.
Oh. Great catch there. So yeah, everyone see my mistake here, folks? I forgot about that factor of 2. Okay. So this would be 2 to the third power, so let's just slow down. We get 6y is equal to 8c1x to the third. But I should be more careful because I did miss that. But when we divide 8 times an arbitrary number divided by 6, we still end up with just this expression, y is equal to some arbitrary number x to the third. And we will get the correct arbitrary number when we plug in our initial condition. Yeah. Does anyone have any questions on that? I did that way too fast, I'm sorry. All right. So now we've got the initial condition 3, 4. So if I were to plug in 4 for y and 3 for x, I can solve for my arbitrary constant. And so I get 4 27ths is equal to that arbitrary constant. Okay, so what we have now is that we've got y is equal to 4 27ths x cubed. What does that represent, folks? The projection of the path of steepest descent. Okay. Notice that this path goes in 2 different directions here. And it would actually give you a cubic, but we wouldn't actually continue that cubic. That's the path that I just found. Now, the next step, and I think I'm going to go ahead and skip it because I've got a hyperlinked solution, is what? This path, as I've described it, if I were to call my independent variable t, and then I call the second variable 4 27ths t cubed, which route is that taking? It's actually taking a route that goes from the origin outward. Do you see that? It's the path of steepest descent. What do I need to do? I now need to modify this through a transformation so that we start at this point and we move to the origin as time progresses. So I'll let you take a look at my solution for how we did that. So take a look at that hyperlink solution for how we did that, how we modify the solution, so we actually move along this path here.
I don't think it's on there.
Is that not hyperlinked?
It's hyperlinked, but I don't think that part is on there, or I could do wrong.
Let's take a look. Not that we better. Doesn't look like it. Okay, then we'll need to adjust it. So what we've found here, folks, is the path of steepest ascent in the xy plane. What is the next question? What's the question after this? Ask you to give parameters of let's C denote the path of steepest ascent. So it looks like maybe, let's see what we do in the next one. So I do it in the next problem, the next part of it. So let's just take a look at this here, folks, and I'll let you copy it over. Here was our path of steepest ascent. Okay, and notice it does certainly when we plug in 3, it spits out a 4, just like we wanted it to. Then what I need to do here is I need to do a transformation. Okay, and to be honest, although you could come up with a way of ensuring that you always get it right before you do the integration, before you solve the differential equation, I think the best thing to do is to get that path. And then kind of the same way I had you do it with the line segments. Remember when I said I want your line segment to start here and end here? You go in and you start modifying that parametric description to make sure it starts at the right point and heads in the correct direction. Okay? You don't have to know, you have to know where it needs to start, which I've given you, and you need to know what's the correct direction, which is either in the same direction as the gradient if you want to ascend, or in the opposite direction of the gradient if you want to descend. So what I went ahead and did was I did the substitution 3 minus t. Do you see how that works, folks? When t is 0, notice that puts me at the ordered pair 3, 4. So folks, all I'm doing is I'm replacing the x right here with 3 minus t here. Okay? That ensures that when I plug in a 0, like my stopwatch time of 0, that I've actually already got a 3 in that position. And then what happens to the x coordinates, or the first coordinate? It gets this expression right here that I'm cubing gets smaller as t gets larger. Do you see that? And you could verify that that's in the direction of the opposite of the gradient rather than in the direction of the gradient. Okay. Once I've got that, how do I actually give the description of the description of this curve up here in 3 space? I guess let me add to this just slightly. What we would do is we'd say, okay, then our curve in 3 space would be our r of t, and it's equal to t, comma, oops, we've done 3 minus t. So we're calling the x-coordinate 3 minus t. We're calling the y-coordinate 4/27 times 3 minus t cubed. And then we put all of this here for the z-coordinate. Yes?
So above, z is defined as 4 plus x squared plus 3y squared. And the 3, is there, what happens to the 3 there?
The 3 should be there.
Okay.
Folks, Chance was mentioning that 3 right there. That factor of 3 needs to be there. Do you see what I'm doing? I'm taking this expression where I see an x, I'm plugging in the 3 minus t. That part had to do with just making sure the parameterization went in the right direction. Then I replaced the y with that expression there in the function. So I dropped that 3 right there. Great catch. Okay. Okay, well, you do have a homework question about this. I'm not going to have you do this on an exam. I find it a little too tough. And solving differential equations is a little bit beyond the scope of our course. Okay? But I do think that this is a skill for you to practice. Okay? Going forward in your math and engineering and science careers, learning this method of gradient descent, I think, is a very important thing. I think you're going to start hearing about it more and more as a skill that they want, especially people going into computer science. They want people going into computer science to know this skill. Okay. All right. Okay, I think that's all I want to say on our 15.5 notes. All right. So now let's jump into our 15.6. Does anyone need a copy of that? Grabbing out your 15.6. Okay. So, in our pre-work, it's been. I think you did the pre-work for this on Monday night, so it's been a little while now. In our pre-work for our tangent planes, we learned 2 different equations for a tangent plane, okay? And it has to do with the perspective that you take. Okay, we can either think of our description of the surface as some z equals f of x, y, or we can think of it as some f of x, y, z set equal to 0. And either viewpoint is valid, but each has its own formula for the tangent plane. So it's really, I think I mentioned this in the pre-work video, you need to know both versions, of course, and the most important thing is to not crisscross them. And that's when I think of mistakes that I see from students during this section, it's crisscrossing the 2 definitions. Okay? So the best way to get yourself uncrisscrossed is to take a problem where you could try it 2 different directions. Okay? So let's take this surface right here, and let's find the equation of the tangent plane at the order triplet 2, 0, 6. And let's see, 12, let's just double check that that points On the curve, yes, that point is on the curve. Okay? Or on the surface, I mean. So, the first way to do this is, let's do it the way we derived it first in the pre-works. Let's go ahead and create a function of how many variables? A function of 3 variables, which means that if you were to talk about just this function right here, we'd be talking about a graph that lives in where? R4, right? It's a 4-dimensional graph. But what am I doing? I'm setting it equal to 0, which is giving me, we don't really have a word for it, but like a hypertrace of this 4-dimensional object. What is a hypertrace of a 4-dimensional object, though? It's a 3-dimensional surface. Okay? So we have this function of 3 variables, so its graph is in R4, but then we're just going to take a slice of it. But slices in R4 don't look like planes, they look like R3. They look like space. Slices of R4 look like space. Okay? That's hard to think about, and if you don't want to think about it, that's fine, but you do need to kind of realize that we're treating this situation as a function of R4, but then we're setting it equal to 0. That still puts us back into 3 space. Okay? All right, so if I were to create a function out of this, we'd have xy plus xz equals 12 minus yz. Let's go ahead and take everything over to one side or the other. Does it matter which side, folks? Does it? We're going to get a normal vector by taking partial derivatives. We get different partial derivatives depending on which side we take it over to. Does it matter? Let's say I bring these 2 terms over to one side, and I then go and start following the formula for this by computing a normal vector. And somebody else takes these over to the other side, and they start following the formula for coming up with a tangent plane by computing a normal vector. We've got 2 different functions, right?
Shouldn't they still be equal, though?
They're not equal.
It would just be opposite.
I think it's because technically a plane can have 2 normal vectors, but they're both pointing along the same line.
In fact, a plane can have infinitely many normal vectors. They're just scalar multiples of each other. So if half the class took it over to one side, they get a normal vector. And in this case, if half the class took it over to the other side, you'd get the opposite vector, pointing in the opposite direction. So we're still good. We've still found a normal vector for a plane. Does that make sense? Okay with that? All right. So let's go ahead and collect everything over to the left. So we get xy plus xz plus yz is minus 12 is equal to 0. Unfortunately, folks, and especially my math lab does this all the time, there's lots of problems where if you forget to take this over, you still get the right answer. But that's not always the case. So do not forget, you've got to create your function f of x, y, z here. So set f of x, y, z equal to the function xy plus xz plus yz minus 12. Our surface, then, is this our surface? Does this f of x, y, z describe our surface? What's that? So this function describes an object in R4, right? What describes our surface? When we take this function and set it equal to 0. Folks, I know you're struggling with this. The reason why I know that the reason why I'm going through it now and really focusing on it is because I found that over the years, that by the time we get to the latter part of the course, it's kind of too late to learn that. So that's why we're going through it now. I know it's a little bit of a struggle. Okay? So our surface is the f of x, y, z equals 0. That is our surface. Is everyone okay with that? Should we talk about that a little more? Now's a great time to talk about it. Okay. So, if I take some z equals f of x, y, let's say I'm talking about this, let's do a different color. Let's say I'm talking about this paraboloid here. Okay? this lives where? The graph of this lives where? Everyone okay with that? Graph of this lives in R3. It's a function of two variables. Its graph lives in R3. Okay. Then, if I look at the f of xy equals 2, where I've set this equal to a number, then what am I finding? I'm finding a slice, and this slice would be this slice right here, where z is equal to 2. Right? And it would give me this curve right here. So where does this guy live? The graph of this lives, well, the graph of that lives in R4, but we could project it down into the xy, or R3, but we could project it down into the xy plane. So we say it like this. The graph of this could be projected so where does it live? Okay. So what I'm saying here is we could now just go back to our regular old xy plane, and we could take that trace. I wish I put it in a different color. Let me. That's fine. Let's do that. Okay. And there it is. There's the graph of that. Okay. So when I'm dealing with this expression here, this is a function of two variables. Its graph lives in R3. So when I take a trace of it, its trace is something that lives in 2 dimensions. Everyone okay with that? This is the analogy. So the problem is I can't take and draw w equals f of x, y, z. I can't take and draw that in R4. Okay? But it lives in R4. And so when I take the trace, f of x, y, z equals 0, it lives where? 1 dimension lower in R3 for this analogy. Okay? We okay with that? Yeah, Jake?
Why 0?
We could have said, well, so what we could have done, for example, and this is where I was actually saying in a lot of these problems, if you forget to take everything over to one side or the other, you could still get the right answer if all you missed was a constant. Okay? I could have created this as my function, minus the 12, right? Then what would be a way of describing the surface? It would be f of x, y, z equals 12. That would also describe my surface. Okay? Well, where it does matter is if I didn't take the variable over, then I'd be in trouble. Yeah. So just like this, I took the, this is the z equals 2 trace. It lives in the plane z equals 2, but there's no, like, we could talk about the plane z equals 2, but we could also just say that's the xy plane by projecting it down. Like there's, so we could look at it as the plane z equals 2, or we could say, well, we'll treat that as our xy plane. Yeah.
Why do you set it to 0 then?
What's that?
Why do you pick 0? That's like general.
Well, because then I'd have to say always leave the constant on the right, and then always set it equal to the constant, and that seems way harder than just always writing the expression of our 3 variables and setting it equal to 0. Yeah. Yeah. Yes.
I just wanted to add, like, hopefully that helps you. Is how I thought of it is like setting equal to 0 means like from 3 to 2 space is like just saying it's just the xy plane that we're taking.
Right. So if we were setting it, this is like setting this would be like setting the function. If we did this, if we took the 12 and set it equal to 12, it's like setting it equal to w equals 12. We still want to draw a connection between that and R3. I don't know.
But if you like to, but like as far as computation, if you took the derivative of both sides, it wouldn't matter.
It wouldn't matter if all you forgot. If you and I do a calculus problem, a differential calculus problem, on 2 different functions, and we're just off by a constant, then as far as calculus is concerned, we're doing the same problem because it doesn't recognize that when we take derivatives. Yeah. Yeah. Great questions. These are tough. All right. So all of that said, this was supposed to be off to the side a little bit. All that said, we can now give our tangent plane as f sub x 2, 0, 6 times x minus 2 plus f sub y 2, 0, 6 times y minus 0 plus f sub z of 2, 0, 6 times z minus 6 equals 0. We'll zoom in on it. So if we compute f sub x as a function, we're taking the partial derivative of this with respect to x, we would get y plus z. And so if we evaluate that at the point 2, 0, 6, we would get 0 plus 6, or 6. And if we compute f sub y, so folks, here's a perfect situation where I don't encourage you to copy me. Just do this on your own. I'm taking each of the partial derivatives, and I'm plugging in the point 206 into each of them. So just do that on your own. Check your answers against me. You'll probably catch a mistake I made. So let's see here. If we do partial f, partial y, we get x plus z. So f sub y, 206. We end up with 8. And if we do f sub z, x plus y, f sub z, 206 is equal to 2. So at long last, what I have for my solution to 1 is the plane 6 times x minus 2 plus 8 times y minus 0 plus 2 times z minus 6 equals 0. And there's the solution to that. Any questions on how we did that? I'm having a hard time reading you these days, folks. I don't know if we're bored or we're lost or I'm doing something wrong or what. Yeah, Gabe.
Where'd the 8 on the end come from? That equals 8?
Oh, that's a 0. That's a 0. And the idea here is, if you're not sure where that came from, when we derived this back in the pre-work, we said we're going to take the gradient of our f and dot it with x minus a, y minus b, z minus c. And the observation is that this is, now this part's actually kind of goes back to what we just said. The gradient is always orthogonal to a level curve if it's a function of two variables. If the gradient is a function of three variables, it's always orthogonal to a level surface. So the gradient is always orthogonal to a level surface. So what we're doing is we're constructing a tangent plane for this surface. So the gradient at any point on that surface is always orthogonal to that surface. Yes? What's that?
Isn't it x plus z in 0.226 for that you said was 0?
So real quick, let's set that equal to 0 because it's a collection of all. A plane is just a normal vector dotted to a vector with a common tail that you're forcing them to be orthogonal. Okay. What's supposed to be 8? What are you thinking? This?
Oh no.
Because this is this 0 right here. Yeah. This 0 right here is this 0 right there.
Yeah. Okay. I was looking at something. Great.
Yeah. No worries. Thanks for checking. Okay. We okay with that?
Yes.
All right. Whew. All right. So let me just go off because I'm writing too big today. So we've got the function. I'm just going to recopy it. I think we had, can you help me out, folks? We had xy.
Xy
plus xz, and then as it was originally given,
Is equal to
12 minus xy.
yz.
YZ, thank you. Great. So the other way we could do this, folks, is rather than thinking about our surface as the trace of a four-dimensional graph, what we can do is we can just give our surface in terms of a variable z. Now, will I always be able to solve for the variable z? No. And that's why the first method in a lot of ways I think is better, even though it's a little longer, a little more complicated. I like the first method better. But in some cases, especially if I hand you a function that's already z is a function of x and y, then you can go ahead and use this alternate definition. Okay. So for me to do this, I'll have to I'll have to solve this for z, so we can have xz plus yz is equal to 12 minus xy. Any questions there, folks? Okay. Factoring out a z, we get z is equal to 12 minus xy all over x plus y. And so you don't have to explicitly say it, but if you want to be able to follow a formula, we'd say that our f of xy is that right-hand side. Okay. So what was our alternate definition then for the tangent plane? Our alternate definition was that the plane would be of the form z. Now careful, that z is not the name of the function. It's the plane already solved for the variable z. Z is equal to f sub x of ab times x minus a plus f sub y of ab times y minus b plus our f of ab. And this has to do with the fact that if I took this format and created my f of x, y, z from this, what would be partial z? Either 1 or negative 1. How are we doing, folks? Okay. So this is our second definition. So you kind of like, you know, if you're not sure where this came from, the first thing I would do is go back and double check the pre-work videos where I derive it. But then the next thing is then you just memorize it. Okay? But the problem is that this formula is often confused with this formula up here. It's easy to confuse those two. Notice I'm using the lowercase for my function of 2 variables and the uppercase for the function of 3 variables. Those are related to each other, but they are different functions here. Okay. All right. So now I just need to compute all these components. So if we go to compute f sub x, what am I going to have to do in this case, folks? Compute f sub x. It's kind of a bummer. I got to do the quotient rule. So the quotient rule says you take the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. Well, I was just doing the Calc 1 quotient rule. I was doing it with a partial derivative, which means that I was treating x as my independent variable and I was treating y as a constant. How does that work, folks? We okay with that? Anyone want to go through that? Okay. So if I go to compute f sub x at the point 2, is 2 comma 3? No. What my
206.
206 was the point, and so for x and y that would be 2 and 0. If I were to do that, let's see here, we'd get, well, this is times a 0, so that's going to die off. Here I get minus 12 divided by 4, which gives me negative 3. Is that right?
Minus 10.
Because we had a tangent vector that could be divisible by 3. Yeah, that works. Right? So folks, everywhere I saw an x, I plugged in a 2. Everywhere I saw a y, I plugged in 0. I think that's what I'm left with. So then we can compute f sub y. And to compute f sub y, it's going to be very similar. We will have the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. So if we evaluate this at the order pair 2, 0, let's see what we end up with. So this would be 2 times negative 2 minus 12 divided by 4. So if I do that, I end up with, let's see, that would be negative 16 divided by 4, or negative 4. How we doing, folks? Thank you. Can I get a thumbs up, thumbs down? I'm just trying to read you. Okay, Andrew. Here we did the quotient rule. We okay with that? Any questions? Then I evaluated it at 2, 0. Okay. So what I'm doing here is I'm following. This is our definition of the tangent plane that we're following. So I've now computed this number. It's going to be minus 3. And I've just computed this number right here. It's going to be our minus 4. Right. So what else do we need to compute? Well, we also need to compute f of 2, 3. So if we go to compute f of 2, 3 back in the original function, we would have, oops, I'm sorry, I don't know why I keep thinking it's 2, 3, folks. F of 2, 0. We would have 12 divided by 2, which comes out to be 6. So now if we just plug everything in, we end up with z is equal to minus 3 times x minus 2, minus 4 times y minus 0, plus 6, which we could clean up as, I'm not going to clean it up. Okay. We'll just park it here. Yes?
Can you go over how you got
I'm sorry, I couldn't hear you.
Sorry, can you go over how you got negative 4 for f sub y?
Yeah, so here was our quotient rule. We good with that? And then I took and I plugged in the order pair. This is f sub y of 2, 0. So everywhere I saw an x, I plugged in a 2. And everywhere I saw a y, I plugged in a 0. Great. Thank you. So folks, one thing that's worth checking is if I were to take everything, if I were to take these two, the x term and the y term over the other side, what would the normal vector for this plane be? What would the normal vector be? Do you see it? Everyone at your table, write down what the normal vector would be and then check with your neighbor. So folks, I didn't put this in alphabetical order. If you put it in alphabetical order, you have 3 times x minus 2 plus 4 times y minus 0 plus 1 times z minus 6 equals 0. Everyone see how I got the normal vector from that? So folks, remember that the way we worked with the plane to begin with was we took some normal vector and we dotted it with x minus a, y minus b, z minus c, and we forced that to be 0, right? That's our equation of a plane. Well, that normal vector would look like n1, n2, n3, dotted with this. Everyone okay with that? Then if I actually do the dot product, what do I get? I get n1 times x minus a plus n2 times y minus b plus n3 times z minus c needs to equal 0. And there I can read, just when I have it in this form, I can just read the entries of the normal vector. So that's what I did here, was I put it into that form right there, and then I read the entries of the normal vector. Did we get the same plane in both cases? Yeah, our planes are, what we're using for the normal vector over here, let's see, way the heck back up here, is the normal vector 6, 8, 2, a scalar multiple of it. So you should see that we have the same plane. I would say, folks, although I want you to get comfortable doing these problems both ways, generally if I give you a, so this is an implicit equation. If I give you an implicit equation, you're best off to use this first definition. And if I give you an explicit function for z, then you should use the second definition. I'm not going to, I think as you go, in the real world, you'll encounter something you want to find a tangent plane of, and you'll have to decide which of the two formulas makes the most sense. But in this class, if I give it to you as a implicit formula, use the first one. If I give it to you as an explicit formula, use the second one. All right. So folks, I don't have anything more to do with coming up with the equations of tangent planes other than that. Okay? I guess I had one comment to make on differentiability. So you need to work tangent plane problems, but there's nothing more to add, right? You apply one of these two formulas to your function. Now I could ask all sorts of new questions, right? Like where is the tangent plane horizontal? Right? Where on this surface do we have a horizontal tangent plane? Well, for a plane to be horizontal, we mean that its normal vector has to only have a z component in it. Does that make sense? If I've got a surface here and I want to say where would I have a horizontal tangent plane, it would be right about here, and you could see that because the normal vector would look like something like 0, 0, some number, right? So you can ask all sorts of questions like we've been asking before, but the only new topic is how do we construct the equation of the tangent plane? All right. So I should tell you that you actually have to be a little bit careful here in that you can always, as long as both partial derivatives exist for an explicit function, you could always build an equation of a tangent plane. But whether or not that actually works depends on whether your function was differentiable there. And that has to do with this discussion about these epsilon errors going to 0, which I don't really want to get into. Okay? But just like we've seen a couple of times in this class, sometimes it's possible to build something in this class that doesn't really work. Okay? So like if I were to have a surface that maybe has like this trough going through it, and then another trough coming in this way, and it has these two troughs. Okay? And so we've got some sort of, trough here and go off this way. If for some reason my surface looked like this, it might be possible, like here it's just a mess, you can't even really draw it. If you've got these troughs, it might be possible that if I approach from the x direction, I can compute the partial derivative with respect to x at the origin. And if I were to come from this direction, I can compute the partial derivative with respect to y at the origin. But it's impossible for me, so that means I could build a tangent plane, but that tangent plane would not approximate the surface at that point. And that has to do with this issue of differentiability. Okay? So first of all, you need to know that your function is differentiable before you can go and construct the tangent plane. Okay. I'll let you guys, did I ask you to copy this one down? I forget. Was it 4?
Yes.
You did? 4 and 7? Okay. If you didn't get a chance to, that's okay. But here I do the video derivation of why this works. And it has everything to do with the fact that the gradient vector always points what? It points in the direction of steepest ascent. That's true. But it's always, I guess I should add to it, it's always orthogonal to the level curves or level surfaces. Okay? So when I'm thinking about this as a function in R4, the gradient always points orthogonal to a level surface. The gradient at any point points orthogonal to it. What I'm saying there is, if I take, say, this paraboloid, like this here, if I go to compute the gradient, so first of all, this would be the function f of x, y, z equals 0. Where does that graph live? So careful, folks. This function lives where? R4. But this trace lives where? In R3. Okay. So this is a level surface. And if I go to compute the gradient of this function, what's the gradient of this function going to be? It's going to be a vector of how many dimensions? Let's see. The gradient of f would be what? It would be f sub x, comma, f sub y, comma, f sub z. It's a vector that lives in R3, right? It lives in the domain space. What's the domain of this function? It's all of R3. So the vector always lives in the domain space. And what does this vector do? It points orthogonal to my level surface. So the gradient on this surface points this way. And that's why it's a normal vector for a tangent plane. Now, folks, a lot of you might just now all of a sudden think, oh, gradient vectors live in R3. Where do gradient vectors live? They live in the domain space. If my function is a function of two independent variables, then the gradient vector lives in R2. If my function is a function of three independent variables, then my gradient is a vector that lives in R3. Here, this is a function of three variables. The gradient lives in R3. But don't confuse this with gradients of functions of two variables. It's so easy to do. How are we doing, folks? Alex.
So the gradient points towards steepest ascent, but since that is a trace of the four-dimension thing, that's why it's pointing off of it?
Exactly. So what the issue is you can't see. What I'm telling you is if you were to take the graph of this four-dimensional object and you were to step in this direction in your domain space, if you were to fly in that direction, then you would be heading in the direction of steepest change in your W values for this graph that we can't visualize. Yes. Yes. Folks, this is going to take a while for you to absorb. I promise you. That's why we're getting to it now. You've got a while to absorb it. Okay? So spend some time. What you don't want to do is just say, well, I'm not sure what's going on. I'll just put that. I won't come back to that. Keep returning to this over and over again. And it's helpful to ask, what type of object am I working with? And where does that object live? You will do better. You'll get a better grasp of this if you're always asking that. Haley.
When you cover up the f of x, y, z equals 0, what are you covering?
Oh, I'm sorry. So what I'm asking you to do here. Let me just go over somewhere off the side. What I'm asking you to do here is I want you to contrast W equals f of x, y, z with f of x, y, z equals 0. Or you could say W equals 0. It's the same thing. Okay? So this is a function of three independent variables. So its ordered pairs would look like x, y, z, w. Okay? This is a function of, there's two ways to view it. The first way to view it is to say I've got x, y, z, comma 0, but every single one of these ordered four tuples has a 0 for the last component. So we go ahead and say that there's no distinction between that and just the x, y, z. So that's why I'm saying that although this is a object that lives in R4, we can think of this as an object that lives in R3. Yeah, thank you for asking that. How are we doing, folks? All right. So folks, if you didn't get to this video derivation of this number 4, go ahead and put a star by it and come back to it. And we also looked at, so derive our second formula from the first. Good. All right. When we come back, folks, I want to jump into the techniques of linear approximation and differentials. There's always a question of how much time should you spend on each of these topics. I just want to let you know that, one, you will get on your next exam, you will have a linearization question and you will have a differentials question. But I stick to the formulas, right? Like if you've got the formula down and you've worked a couple of these problems, you should have these, because there's just too many topics in this course to spend a whole lot of time on these two topics. Okay? So we'll pick those up when we get back. I've got it as 3:47, sorry to run a little long. If we could start back up at 3:58, that'd be great. So we're now going to look at linearization and differentials. And in my opinion, there is no real change in these problems from the way we encountered them in Calc 1. The only exception will be at the very end, I'll show you a couple of ideas about linearization that we're not going to get into. But you can see how you could extend it to higher order surfaces. So I think the best thing you can do if you don't feel like you know what's going on is not to look at these as problems in R3, but to look at them in problems in R2, which is what we did when we did them in Calc 1. So there's a link to the notes that I give when I do this in Calc 1, as well as the videos that walk you through those notes. So I would recommend taking a look at those if what I explained just now doesn't make sense. Okay? The basic idea is that just like in Calc 1, our goal is to take some function and at a particular point approximate the curve with a line, right? And why is that beneficial? It might be that, maybe we don't know what that function is entirely. We just know the behavior at a point or something like that, and its derivative. Or it might be that we do know the function, but working with it is very computationally intensive or really messy. Regardless, what we'll say is that if I want to know what is the y value on the function a little ways away from that known point, rather than finding that y coordinate on the red function, we instead find the y coordinate on the green tangent line, and we say close enough. A good enough approximation for what we're doing. Now, obviously, you can't go too far out. You can't look too far out away from that x coordinate that you originally built the tangent line from and still have a good approximation, right? If this red curve continued to rise, then we sort of get an error that continues to get bigger and bigger. So we can't go too far with that, but the phrase is locally around this green point where we created the linearization, around that point we can approximate functional values. So the idea is the same in when we've got functions of 2 variables, which we can draw, or even functions of 3 variables, which we cannot draw. We can still approximate the functional values through this linearization formula here. Now, I think that this shouldn't feel all that different. What does this look like to you, this linearization formula? It is just the equation of the tangent plane, so please don't think of it as, oh my gosh, I got another formula to memorize. It is just the equation of the tangent plane for the version that was in the form z equals f of x, y. And so the picture that goes with this, and again, I think this picture quickly gets way too cluttered. And it's a lot easier to see the stripped down version from Calc 1 than to try to look at the 3-dimensional version in Calc 3. The idea is we know all about this point. Let me put it in red. We know all about this point right here. We know its domain. We know the domain value that we're interested in. And we're assuming we know what its z coordinate is. Okay? So we're able to find everything about that position. Okay? Then we're going to assume that we can compute, for whatever reason, that we know the derivatives, the partial derivatives at that point. From that, we can construct the what's drawn in pink here, that pink tangent plane. Okay? So it's a messy diagram. We've got the gray surface. We've got a pink tangent plane there. Okay? So what I'm saying is if we wanted to guess, if we wanted to look in the future to see what's happening at this arbitrary xy coordinate in the domain, if we wanted to figure out about what is its z-coordinate, its actual z-coordinate is this height right here. This is its actual z-coordinate, right? And if we wanted to approximate what that z-coordinate was, instead of trying to plug it into the function for various reasons, maybe it's computationally intensive, or I'll give you another reason here in just a second, instead of plugging into that function, what we could do is we could plug it into the tangent plane equation and say that this z-coordinate is close enough to this z-coordinate. Now, obviously, to make the picture work, they had to spread them out a little bit, right? Otherwise, the picture would just be too messy. It's already messy. Okay? But what we're saying here is that this z-coordinate, which we get by computing, sorry, my lines look different. So if we want to know what that z-coordinate is, right? We want to know that coordinate of this order triplet, of this point right here. We know the x and the y. We want to know what its z-coordinate is. Rather than coming up with that z-coordinate, we come up with this z-coordinate right here, which is the z-coordinate corresponding to the point on the tangent plane. And we call that a good enough approximation. And we could get into more interesting questions like what is the percentage of error and stuff like that. Those are all kind of interesting questions that you can extend this on. But this topic, this course is broad enough, so we're going to kind of just focus on doing these linearization problems and just using them to compute functional values. Okay? The way I try to sell this to students when I teach it in Calc 1 is I basically give them a way of approximating. I try to sell it in Calc 1 by saying, hey, let's approximate the square root of 16 let's not do 4. Let's approximate the square root of 16.5 using linearization. Okay? So we've got we can think of this as a function f of x is the square root of x. So we've got a nonlinear function here. And rather than computing, rather than plugging 16.4 into this nonlinear function, what we do is we construct the equation of a tangent line of a point near that. And then we get the output value on the tangent line rather than the output value of the function. Because we all know that the answer to this should be somewhat close to what? 4. It should be a little bit more than 4. The question is as my x-coordinate increased by 0.5, about how much should that affect my f of x coordinate? And that's what linearization does. That's how I try to sell it to my students in Calc 1 to convince them that this is a worthwhile endeavor. The real way you do this is what? The real reason for linearization is what? In the real world, seldom does somebody say, here's a function, go do some work with it. Right? In the real world, seldom are we given a function. So it might be, if you go back to that first introduction to multivariable functions that we gave, where we talked about temperature and wind speed, and we computed wind chill. Okay? In reality, what you do is you gather data points. And if you can say at this, given this temperature and this wind speed, we know this is what the wind chill is. And we know how the wind chill changes if we adjust temperature at this point. So we let's see, I'm trying to think of a multivariable example. This is a little hard for me to do. So let's bring it all the way back to just a single variable example. Okay? If at 12 o'clock I go and measure the temperature outside, and the temperature is 70 degrees, and then at 12:01 I measure the temperature outside and it's 71 degrees, then I've got both the current temperature at 12 o'clock, and I can approximate how it's changing, and from that I can build a linear model and predict a little ways into the future. All of that I was able to do without actually knowing a function that governs temperature. Now that model's not great. It can't look that far into the future, right? So that's what I'm saying here, is if you've got some quantity that you want to measure, some functional quantity, and you know that it depends on two different inputs, you could go out into the field and you could gather some data. Given this input and this input, what is the output? And then if you could somehow measure how it's changing, like you come back an hour later, or you come back 2 days later, or a year later, and look at how it changed over that small increment of time, then although you can't actually construct the function, because it's probably a nonlinear function, most things in life appear to be nonlinear, you could construct a linear function in order to make small predictions into the future. And if it's an input of one variable, then your linear function's a line. If it's input of two functions, your linear function is a plane, which you can look a little ways into the future. So actually what I'm saying here is when you do this problem, because a lot of you might be saying, that seems like a lot of work. Why don't I just put the x and y coordinate into the function? It's because you can actually do this whole process of linearization without actually knowing what the underlying function is if you're gathering data. Right? And that's how you would make predictions looking into the future. There's other applications of it. Error applications are a great one, right? Like if I know that, let's say we've got the area of a rectangle. Let's do the perimeter of a rectangle, right? The perimeter of a rectangle is equal to twice the length plus twice the height, right? So I go out and I measure a rectangle's length, and I measure, let me call it width. We usually call it width. And I measure a rectangle's width, right? My instruments are going to have a little bit of error in them, right? The question is how does that error compound when I compute the perimeter? And doing linearization and doing differentials is a way to kind of approximate those compounding errors. Okay? So that's another example of why you would use these. Okay? But to be honest, folks, when I made your last test, I ran out of computer memory making some of your graphics. And I've got 64 gigabytes of RAM. Okay? In reality, doing computations, if you're doing them by this old brute force way of doing computations, you can quickly run out of memory to do something. And so rather than doing nonlinear computations, if you can give a linear approximation that's good enough, that's the way to go. So there is a sense where this might be too computationally intensive to work with. Okay? All right. Oops, what just happened here? Where'd we go? Just scroll down. All right. So this problem here, and all these have solutions. Let's go ahead and do this problem here. We want to find a linear approximation of the function f at this point. Okay. So to be honest, I don't really have much else to do other than say follow the formula. Okay. We said that the formula for the linear approximation at some ordered pair AB of x, y is equal to f sub x of AB times x minus a plus f sub y of AB times y minus b plus some f of AB. Folks, did I just give you a brand new equation to learn? No, it's our tangent plane, but instead of thinking about it as a tangent plane, I'm thinking about it as a tool that gives me a linear approximation to the output values of this function. Okay? So all we need to do is we need to go do some computation. So f sub x of xy is equal to, let's do the power rule on this, so minus 5 all over x squared plus y squared squared, and then we'd have times a 2x by the chain rule. And if we do f sub y sub xy, we'd have minus 5 times 2y all over x squared plus y squared squared. Folks, I did that a little fast. You want to keep working with your partial derivatives. what I did when I did this, when I computed this, is I thought about it as 5 times. This is, you guys remember doing this trick all the time in Calc 1 to avoid doing the quotient rule, right? Okay. So then I took the derivative of that with respect to x, and there's a chain rule in there, right? So you bring down the exponent, subtract 1 from the exponent, and then multiply by the derivative of what was inside of that expression. How are we doing? Anyone want to talk about it? Love to talk about it if you'd like to talk about it. Going once. All right. So then we can find f sub x of, we're doing this at the ordered pair, the domain value is negative 1, 2, right? And so that would give us, that looks like 10 all over 4 and 1 is 5, which comes out, oops, 5 squared though, right? 5 squared. So we get 10 over 25, let's do it, 10 over 25, 5 goes in each of those, so 2/5. Okay. And if we do f sub y of negative 1, 2, that's 4, that's minus 20, the denominator hasn't changed, so we end up with minus 4/5. Then we're ready to give the linearization as a function. So our L, and folks, this is my own notation. I think it's because I might construct many linearizations to the same function. I always like to give the ordered pair that I constructed the linearization about. There's other ways you could do that, but I just like to always do that. I call it the linearization at that point. If you don't do that, my math lab won't do that, most textbooks won't do that, but I always like to know where I just centered the linearization. I call it the anchoring or the centering of the linearization. So I like to always put that there. And that's equal to, we said it was 1/5? 2/5. And the signs were good. 2/5 times x minus x plus 1 minus 4/5 times y minus 2 plus, I'm putting f of AB here, but I'd already told that to you, right, folks? So 1, so plus 1. Andrew, you had a question, or was that just scroll down?
I figured that.
Great. How we doing, folks? I don't think there's a whole lot to this topic. It's a good one. It's a good 3 points on a test, I feel like, as long as you practice it 2 or 3 more times. Don't assume that you've completely got it down. You need to practice it a couple times, but there's not much more to say. What I'd now like to do, I guess I gave us, never gives you enough room, and then all of a sudden, way too much. Okay, let's use this linear approximation to estimate this value right here. So we're going to say that f of negative 1.05, comma 2.1 is approximately the linearization centered at negative 1, 2 of negative 1.05, comma 2.1. Where's that approximation part coming in from, folks? Why do I have that approximation symbol?
Because it's not the exact number.
It's not the exact number, because what this output value is going to land where? It's going to land on our tangent plane. This is going to land on the surface. Okay? So we're off a little bit. That's why it's approximate. That goes to this idea of this picture right here. We're going to find the blue z coordinate, the z coordinate of this blue point, not the z coordinate of this blue point. But they're close, relatively. Okay? So we take our answer from before, which I think we said was 2/5 times x, so negative 1.05 plus 1 minus 4/5 times 2.1 minus 2 plus, was it 1?
Yep.
1. Okay. And this is, I don't know, not impossibly hard to do. What do we get? Negative, is that 0.02? I'll need a hand, folks, because I'm getting tired.
0.02.
Negative 0.02.
Minus 0.08 plus 1.
Minus 0.08 plus 1. And so 0.9 is what we end up with. let's see how we did. In your calculator, take the actual function. I guess the important thing to recognize is this is a nonlinear function, and we're going to plug in 5 over 5 divided by negative 1.05 squared plus 2.1 squared, and approximately, just approximately what do we get? .907. Okay. That's still a rounded off answer from the actual answer, right? Did you round it a few decimal places, or is that exactly what it came out to be?
Well, I mean, there's like 5 more decimals.
That's fine. That's fine. Yeah. So this is still approximate, but it's what we're using as our stand-in for the actual answer, and it's close to our approximation value. Let's load that in Calc Plot 3D. So here you can see in red, I have plotted the graph of our function. You can see that we've got that domain value down there, the domain value negative 1, 2. Everyone see that? There's the point on the graph of this surface. And let's go ahead and first turn on our tangent plane, which should be this right here. There's our tangent plane. And sorry that, it looks kind of messy because it's just the interaction of the surfaces, but there's our tangent plane that we computed. We're going to use that as our linearization. So just to reiterate, what we're doing is we said, okay, we want to know what is the z-coordinate of this point right here. We don't know what its z-coordinate is. That's the point that's actually on our red surface. We want to know at, sorry, let me go ahead and put that point in here. Do I have it? I should. Q star, that's it, that's what we want. So at that domain value right here, so this blue domain value, it gives us this point on our red surface, but we want to know what its z-coordinate is. But instead, what we did was we plugged that point into our, boy, it's not the prettiest thing in the world. There it is. We plug this, see it? To the point where you can see it. So we plug the shifted point into the linearization, which landed us on the tangent plane, and the z-coordinate of that tangent plane is very close to the z-coordinate that we were looking for. It's not the best demonstration, but it's still a leg up on what we had. Okay. Everyone see that, what we're doing? Do you have a sense of what we're doing with these linearizations? So it really is sort of a plug and chug problem, and I don't have a lot more to add to that. The next thing I want to point out is we could just focus in on the change in the output values. Remember when we were talking just a moment ago about you take a measurement, maybe you measure the radius of a circle, or let's take a cylinder. You measure the height of a cylinder and you measure the radius of the cylinder. Both of those inputs could be wrong by a little bit, right? There's a little bit of error there. And we want to know how is that, if we made the maximal error, if the error was as bad as it could be, how would that affect our approximation of the volume? And so that would be, rather than focusing on what the actual volume is, we're focusing on the error, right? When you're going to say, I think the volume's 20, you want to know how accurate do you think that 20 is? Okay, so you need to know what your maximal error could be. So rather than figuring out on actually what the volume is, or think what's the potential that we're off when guessing what the volume is. That's what we want to focus in on. So differentials is a great tool for that. When we did this, so again, I think that this is a rough place to try to learn differentials. The best place was back in Calc 1, and then we just, rather than doing differentials with a function of one variable, we do differentials on a function of two or higher variables. Okay? So here's our formula for the differential. The thing I want to point out here, folks, is this is the actual change in z. So this is the, let me say it like this, this is the f of, let's see here, we're using, this is our f of x plus dx, comma, y plus dy, minus our f of xy. The delta z is the actual change in the z coordinates that we could compute. Okay? So I take some xy ordered pair, plug it into the function, that gives me a z coordinate. Then I nudge them, I move slightly off of them by some differential amount, and I plug them into the function, and it gives me another z coordinate, and the difference between those is called delta z. But delta z might be hard to compute for various reasons. Okay? Or maybe it's unknown for various reasons. Okay? So instead of computing delta z, we compute differential z instead. Okay? And so differential z is just the, look at what it looks like, folks. Look what it looks like.
Kind of looks like the plane.
It looks like the equation of the tangent plane, except it's missing the plus the f of x, f of the original f of xy. Why? Because if I'm looking for the change from where I started to where I ended up with, this would have a plus f of xy, and we would subtract an f of xy from it. Okay? So, folks, I don't think it's worth going into a diagram for this. Instead, I would recommend going back to the Calc 1 introduction to differentials. Okay? And don't be too cool for that. It's always good to go revisit something. Okay? All right. So in this case, look, I'm going to do a differential, in fact, of how many variables? Differential on a function of how many variables?
4.
We're going to do, well, we're going to do for 3 input variables. It'll be the function is a graph that lives in R4, but it's an input of 3. So let's do both the linearization and then the differential for this. So this part's the same thing that we saw before, and I'll take a hand with it as we compute it. So we're going to say our L of x, y, z is equal to partial f. Let's use the subscript notation. F sub x at the point. Let me just do that. I'll just write it like this, times x minus pi over, let's see. I really don't want to write this whole thing out. All right, let's go ahead and, I'm not going to give you the formula for it because we're just following it. Our f sub x in this case would be what, folks? For our function here, what's our partial derivative of that with respect to x? Yep, that's the cosine of x plus y minus z. And so if we find the f sub x at that point, so folks, what I'm trying to avoid is having to write that point 5 times. Okay, so at the point, what's f sub x? It would be the cosine of pi over 6 plus pi over 3 minus pi over 3, right? And that would be the cosine of pi over 6, which is what? Other one? Radical 3 over 2. If I compute f sub y, it's actually the same partial derivative, cosine of x plus y minus z. So if I do it at the point, we'd have f sub y is the same square root of 3 over 2. So folks, I'm being a little sloppy in the notation because I just want to get through this example. So I'm not writing of the point. Does that make sense? Then I would have f sub z, which would be, careful, there's a chain rule in there, so it would be minus cosine x plus y minus z. And so f sub z at our point is minus the square root of 3 over 2. How we doing, folks? So we're building this linearization. We're building this linearization at the point pi over 6, pi over 3, pi over 3. And that would be the square root of 3 over 2 times x minus pi over 6 plus the square root of 3 over 2 times y minus pi over 3 minus the square root of 3 over 2 times z minus pi over 3. What do I have to add to this, folks? The sine of pi over 6, right? That's the functional, that's the output value at the point pi over 6, pi over 3, pi over 3. And so that's plus 1/2. So what was that? That was the f of pi over 6, pi over 3, pi over 3. So folks, is this a tangent plane? Well, depends on how you want to call it. This is actually a tangent hyperplane, right? So the graph of this function, the graph of this sine of x plus y minus z, where does it live? The graph lives in R4, and so we are approximating this, we're approximating the graph of this function with a hyperplane, a four-dimensional plane. Now, we don't have to visualize that to be able to see the value of being able to approximate it. Instead of plugging x, y, and z coordinates into this function, we plug the same x, y, z coordinates into this function and look at all of our computations. They're all addition, subtraction, and multiplication, as opposed to evaluating a trig function. So in this example, I should have prefaced this. In this example, I wanted to do a linearization of a function of 3 variables, as opposed to the first example we did, which was a linearization of a function of 2 variables. How are we doing, folks? So then here I'm just asking you to use differentials to approximate this expression right here. So so what we really want to know is what delta W is. But we can't find delta W. That's the actual change in the W coordinates. So instead what we do is we say that's approximately differential W. So whenever you're talking about the dependent variable and you've got a differential, that's on its equivalent tangent object. A tangent line, a tangent plane, a tangent hyperplane. Okay. And so we'll say that that is equal to, and I don't want to copy out the original point here, so I'll just put f sub x of, we'll just put ABC times differential x plus f sub y of ABC times differential y plus f sub z of ABC times differential z. So notice that this part is exactly the same as before for our problem. That's taking the partial derivative with respect to x and evaluating it at our point. So that's still going to be the square root of 3 over 2. And then in this case, our differential x is this 0.1 here. Everyone see where I got that 0.1 from? Oh, I'm not sure. Let me put it right there. It's that 0.1 right there. Plus f sub y, which is the square root of 3 over 2, times this 0.1. Oops, that should be what? Negative 0.1. That's this one right here. plus the square root of 3 over 2, minus the square root of 3 over 2, times 0.05. Could I get a decimal approximation of that, please?
0.6299.
So I'll put approximate, that's point what?
6299.
So let's call it 0.630. So that is not the new that's not what I'm predicting the new output value to be. What is that predicting? What is that supposed to be predicting? The change in those output values. Okay. That is, I'm saying if you plug in, so we already know that f of pi over 6, pi over 3, pi over 3, that was what? What was that, folks?
1/2.
That was 1/2. So,
I messed you up. That is the one including 1/2. I looked at the
oh,
wrong.
subtract the 1/2?
Yes, that right there is our output value. So if we subtract 0.5 from it, we'll get the.
So 0.030?
130.
130? Oh, thank you. Yeah, 1.130.
Yes, sir.
Great. So we already know that f of pi over 6, pi over 3, pi over 3, we already knew that that was 1/2, right? And so we're going to say that f of pi over 6 plus 0.1, comma, pi over 3 minus 0.1, comma, pi over 3 plus 0.05, that is approximately that same 1/2 that we had before, plus our differential w, which is what we just computed. So it's going to be 1/2 plus 0.130, which is where we get our 0.630 from.
That last bit is just the same as plugging all that into the tangent plane, though, right?
Correct. Correct. The other way we could have gotten that was to plug each of these actual the entire value of the ordered pair into the linearization, and it would have given us the same 0.630. I tell my students in Calc 1 that linearizations and differentials are just two sides of the same coin. They're just two different perspectives of looking at the same thing. One focuses on the change, one focuses on the new value, but you can't have one without the other. Okay, folks, I'm not gonna lie, I find this kind of tedious. It's something to work through, and I promised that you'll have a linearization question and a differential question. When I ask the differential question, usually I just focus in on this part right here, and I don't worry about adding it to some other output value. But I wanted you to see this question because this one shows up in your homework. Okay? All right. What I'd like to do is point you in a direction where you may go in subsequent math courses or subsequent physics and engineering courses. Okay? Hopefully you remember that in Calc 2 we introduced Taylor series approximations to curves. Okay, so I want to just give you a quick review of that. Suppose I've got that blue y equals sine of x function. Okay. Well, in Calc 1 actually we learned how to fit a line to that blue function. That was the linearization that we did in Calc 1. We put a line to that blue function there. Okay? But then in Calc 2, you realize, okay, but you could do the Taylor series. You could approximate the sine of x with a Taylor series polynomial of degree 2. So what you did is you computed, where is it? Oh, I guess not 2. You do these as odds. So 2 doesn't really help because the second term is 0. So you could do a quadratic, but then you have to go to the third degree. So if you did a third degree, then this is a cubic function that approximates the blue sine curve. And notice that oftentimes, I think always, that the cubic is a good approximation for longer than the original line was. and then you come up with a 5th degree, etc. And as we take higher and higher orders, our new polynomial becomes a better and a better approximation for that function. Okay. So what were we just doing with tangent planes? We were taking surfaces that live in, let's go stick with R3, surfaces that live in R3, and we were approximating the surface with a tangent plane. But why not approximate it with a tangent paraboloid? Or then higher order surfaces. Okay? So that's the way we extend this idea in higher dimensions. Okay? So what I get here is our book does not go through this. I went ahead and pulled this from another book. Here was Taylor's formula for coming up with coming up with however many terms of your Taylor polynomial. So this was the way we came up with those. So there was this part right here is just your linear approximation. This was a quadratic approximation, and you could take it up to an nth order polynomial to approximate your curve with. Okay? There's a question of how good is that approximation, and that's not something I'm getting into now. That you did a little bit of that in Calc 2. Okay? But then we see we can extend this to higher order dimensions. Now, part of this should look like stuff we've already done today. Which part of it? Here I'm going to say that, let's see here, what was this Taylor's polynomial? So if I want to come up with a Taylor polynomial centered at, what does it say it's centered at the point AB. I see. Why I didn't use x and y on that, because you could have. They're using x where we've got it, where we would have an x, we've got an h. Where we would have a y, we've got a k. So look at this part right here, folks. This part right here is the tangent plane approximation to a surface. Okay? Then you could take and you have to then add in these 3 factors right here to get a. Now you've got like a sort of like a paraboloid approximation to a surface. Okay? So you can go ahead and work through the, take a look at these. I'm not going to have you do anything with these. I just stole them from a book. But I want to show you essentially what we were doing. Okay? So if we have this surface right here, what we had been doing was approximating the surface with a tangent plane. But if you take Taylor's formula and extend it further, okay, and the way you extend it further, you don't need to go back. The way you extend it further is you've got 1 over 2 factorial. That's that same 1 over n factorial that showed up in the Calc 2 version of this. Okay? And then here you've got a quadratic times your second derivative evaluated at a point. And another quadratic times another second derivative at a point. And another quadratic times another second derivative evaluated at a point. That's the same as that second term when n gets to 2 right there. So I think that's all I want to say about that, but I want to point that out to you. We don't do this. I don't think the other Colorado schools do it, but depending on where you go, you might be asked to have seen this in Calc 3. So I'm not going to do it justice, but I want to point this out to you that when they talk about higher order Taylor polynomials, okay, what you're doing is you're just doing the Calc 2 Taylor polynomial, but you're doing it for a function of 2 variables, or you could actually take it higher than that to functions of 3 or 4 variables. And so you're coming up with polynomials that approximate surfaces, but they're not polynomial in the line on a board sense polynomials. Okay. If you're worried about, what from these last couple of lectures do I need to focus on? Okay. The first thing is go back to the problems that we worked in a pre-work. If we worked a problem in a pre-work, then that was one that I said that's definitely something I could just show you in a video and expect you to then be able to do going forward. Okay. The next thing you could start doing is you can go ahead and start looking at the exam review for exam 2 and start looking at the gradient problems that show up on that. Okay, the gradient and tangent plane problems that show up from that. There's a lot, hopefully you see that these last 2 sections, There's a lot of potential topics that you could dive deeper in. I've tried to point you in the direction of a couple of those, but we're not going to go too much deeper in anything that I haven't stressed. All right. I'll figure out how we're going to do this. I'm going to go ahead and extend your 15.7 MyLab Math. I just put it up before class, but we've not covered 15.7. So all you have due this weekend, is 15.5 and 15.6 MyLab Maths. Okay? I'm thinking that these last two topics from this chapter are maximization problems and Lagrange multiplier problems. I'm going to just figure out where I can fit those in. Because what I'd rather us do is get into the topic of multiple integration. Okay? So, for next time, you've got one of your most important pre-works. So folks, if you do not do this pre-work and you come on Tuesday, which you should still come even if you don't do it, but if you don't do it, you're going to be in a world of hurt because the whole world will have changed on you over the weekend. So make sure you work through. Oops, you don't need one, Jay, sorry. So here's a. Who needs a copy of this? Yes.
I walk in on it and I'm like, what are you doing?
So here is your multiple integration. Okay. So just showing you where we're going, you can take a look at the picture on the first page there. In Calc 1, we found areas between a curve and the x-axis. Here in Calc 3, we're going to be finding volumes between a surface and the xy plane. And that's what we're setting up for in this next pre-work. Okay. Folks, I know that today felt a little bit scattered. Okay, we had to touch on a lot of things. You'll see that when we get into chapter 16, everything will start feeling a little more cohesive again. But if you have any questions or concerns, stick around. I also have office hours starting here at 5:30. 5:15 to 6. So if you want to stick around and ask some questions, you're welcome to do so. All right, take care, folks. Yes, it will be in B1317. Yep. So if you want to go there now, and I'll show up at 5:15. I don't have office hours on Fridays, but and I could maybe do something tomorrow afternoon, if that works for you. Okay. But feel free to shoot emails, and I'll certainly take a look at those. Yeah.
I have
Yes,
one
Ben.
question on the notes. So here you added the 1/2, which was the sign of
We evaluated it at our point.
right, but why did you add that to the end of this?
Oh, so this is for the linearization. This is the differentials, which doesn't have it. For the linearization right here, we do have plus that value.
Oh, okay.
Yeah.
Okay.
So in my first
So you're
example,
fine.
we did this one. In the sign example, we did this
Oh,
one
okay,
here.
that's why I was thinking that we were following.
Yep. And the way you should think about it is, it's a functional value plus the change in each of the three partial derivative directions.
Okay.
Yeah.
Thank you.
Yep.
Might be a good idea.
Matthew, do you have a second?
Yeah.
Great. Stick around.
I
Haley,
like
what's
your
up?
shoes.
Oh, thank you.
Every time
Yeah.
I see these black shoes, I'm like, oh, whoa, those are cool, and I never
Oh,
tell you.
oh, thank you. I appreciate that.
Yeah. So I had to write on my hand today, telling nice shoes.
Oh, well, thank you. Thanks, Haley.
Yeah.
Christy, did you have something?
I was just curious if there was another business card left.
Yes, there is. Yeah. So take a look at it. You're welcome to take a picture of that. There's also data entry on the back or data collection. I don't know what that consists of.
Those kids in high school come to my coffee shop all the time, which is kind of funny.
Oh,
From
do
the
they?
academy.
What coffee shop are you?
It's Caribou. It's by 120th and Federal.
Oh yeah, I know that one. Yeah.
But they come on every time around 3 o'clock.
That's really fun.
Yeah. I'll have to bring that up to them.
That's cool. Huh. Matthew, you had mentioned. I got some more information about what exactly does it take to be a club advisor,
Yeah.
and it turns out there's not a lot
Really?
of work on my end because I basically just. So anyway, if you're still looking for somebody,
I think so. Yeah.
I'd be interested in doing that.
That's awesome.
Yeah.
Thank
Yeah.
you. Yeah. I'll text the creator of it. I haven't caught up with him in the past week or two, but It doesn't look like we have like anyone yet. So
Okay, yeah.
I think that'd be perfect.
Yeah, that sounds good. So, I don't know who's going to like whether you need to talk about it and decide. But once you feel like anybody who's interested in doing the bug is interested in me being the advisor, then I'll go figure out what I have to do.
That'd be awesome.
Yeah,
I appreciate it.
Cool.
Thank you
Yep.
very much.
Uh-huh. Yeah, it'd be fun.
Yeah, definitely.
Yeah, like I said at the beginning of the semester, it sounded interesting, but I just couldn't commit to it. But
Yeah, I
after
understand,
hearing
like,
what the
workload
is, it sounds like it's not too much on my end.
Sweet.
So yeah.
Okay. Yeah, I'll keep you updated then.
Sounds good. Sounds good. All right. Yeah. Take care. Have a good trip, Christy.
Thanks.